Welcome this morning to the talk Beyond Containers, Why MicroVMs Are Essential for Multi-Tenant Workloads. I am Alex Zenla, the CTO and co-founder of Edera. We still have some people coming in, which is nice. There's only a few seats left. Who am I and why am I here talking about this? I have been involved in open source since I was quite literally a child. I think my first technically open source contribution was when I was 11 years old. I've been involved in all the projects you see on this slide here. Got started kind of in Linux early on, basically because I couldn't afford Windows, and kind of built upon that a variety of different disciplines and interests. Despite the fact that I started in the Internet of Things when I was 14 years old, working at a company in Oakland, California, my actual interest has always been in virtualization, systems engineering. To be honest, that was the reason why I was interested in the Internet of Things, is because it's usually edge devices and things like that. So you see all my interest here. You might wonder what all connects them. Genuinely, it's just I like to break things and mess with things. So I guess an important point as I talk about everything in this talk is that I am not unbiased. The virtualization, MicroVMs, this is basically my life's work at this point. Edera is a company focused on that, so we're going to talk a little bit about Edera, but we're not going to just talk about Edera. We're also going to talk about the general problem, why people care about this, and it's likely that I will be shorter than the allotted time because I thought it was 30 minutes and it's actually 40 minutes. So if I speed through this, well, lunch is right after, so you'll be fine. Also, one thing is some of the content here was actually not written by me. Originally, the presenter for this was going to be Lewis, but he couldn't make it, so I am standing in his place. So what is container isolation really? Well, there's a fundamental problem with containers, and although this might be Open Source Summit, it's actually incredibly interesting to realize that everyone runs a container these days. There used to be a time when KubeCon, Cloud Native Con, it was maybe, the weird people over there running containers. That's no longer the case. Everyone's running a container. You're likely running multiple of them on your machine today, even if you have Mac OS or something like that. But the fundamental problem with containers is that they are not a security boundary. A container was originally designed for ease of use and packaging. If you really look at what Docker is all about and why arguably Docker won the container race, it's primarily because of the ease of packaging, the Docker file, all of those things. And the way that people tangentially talk or touch containers rather is usually through that mechanism. And so the vast majority of people really care about that packaging reality. But containers as an actual concept in the Linux kernel don't quite exist. Realistically, a container is, in its most simplest form, a namespace, it's actually multiple namespaces, which is effectively a way to segment the parts of what a process can see. So we have a PID namespace, a network namespace, a mount namespace, user namespace, IPC, UTS, and I'm sure there'll be more in the future. And that is kind of the fundamental building block of the actual security mechanism. Most people, when I ask them what a container is, will only mention cgroups. But cgroups have nothing to do with security. They're all about resource consumption. How you actually isolate resources, and I say isolate, not really isolate. It's how you account for resources. Most people that I talk to will only ever mention the cgroup part. A lot of people don't even realize about the namespace side of it. Importantly, when you ask the Linux kernel to create a container, you actually don't ask it to create a container. You create a C group, and then you also create a whole bunch of namespaces. But the way that you actually create a namespace is not through like some cool mechanism. It's literally just you unshare your namespace that you inherited from someone else. So these two concepts are what we consider a container. Of course, there's also packaging, OCI, other stuff on top of that that creates the container that we actually know and maybe love. But the fundamental concept doesn't exist in the Linux kernel. But fundamentally, the problem with a container is that they're just processes. They share a single kernel, a single Linux kernel. Importantly, Linux is a monolithic kernel. It is effectively one giant process running in kernel space. Any sort of namespace or C group concept thrown on top of that is effectively not really enforced through any sort of proper security boundary, but is more of a suggestion that things in the kernel have to opt into or really understand. There's nothing fundamental about the architecture that provides that actual security. And yes, the kernel has no concept of a container. There's really nothing called that. In fact, some people think that the C in C group stands for container. It actually stands for control groups, the ability to control the resources. Importantly, though, namespaces are not isolation. Effectively, a namespace, when usually combined in the way that a container would, it gives its own view of processes. The PID namespace, as an example, its entire goal is effectively to create a process list that only you can see what processes you create are the ones that you allow to join the namespace. Many systems will basically give you PID1. PID1 is the start or the init system inside of Linux. If you start Linux today, systemd is usually your PID1. But inside of a container, you take over that responsibility. There's also things like container init that kind of take that over and kind of give you like a mini systemd. Systemd also has like systemd in systemd, which is a whole thing, but no one seems to really do that often. I want to say like Podman maybe does that, but most people aren't running Podman in my experience. But it also gives you private mounts and network stacks. Although the word network stack is maybe a little bit misleading because what it actually gives you is network interfaces. So effectively, once a packet leaves a network interface that's inside of a namespace, it's just in the standard Linux network routing system. Now you might have your own routing tables that are isolated in the namespace, but ultimately if a network driver inside of the Linux kernel sees your packet, it doesn't have any clue that it came from one namespace or the other. If you pass in a network interface into a network namespace that your process sits in, that packet effectively just escapes onto the shared Linux kernel. And of course, the way that we practically do networking, by the way, in containers with CNI is like a whole nother aspect of weirdness because the packet sort of escapes out through a virtual interface onto the shared host. And then at that point, you have quite literally broken the ability for people to like execute code outside of your network namespace if that packet is processed by the wrong thing. And importantly, the reason why we kind of did containers this way is primarily because they're cheap, fast, and we didn't like virtual machines at the time. Virtual machines were usually associated with like VMware or, God forbid, QEMU or something like that. And those kinds of projects, like they feel heavy weight. They feel like a lot to deal with. And so containers kind of provide this thought of like, oh, you have virtualization, but without any of the actual virtualization. Importantly, what they don't do, though, is they don't isolate the kernel itself. At the end of the day, when you make a system call with a process that's running in the namespace, it basically just carries around a structure that contains what that namespace is, but it's up to each individual function in the Linux kernel to actually know that it's in the namespace. There's actually a very interesting case that I like to talk about of where namespaces don't help at all, or cgroups for that matter. If you ever run Btrfs, Btrfs has these async workers that run inside the Linux kernel. Those async workers are shared across all of the different processes on the system. There's no separate Btrfs process that's handling your request if you're passing in a Btrfs file system into a container. Well, if there's a bug in Btrfs, you can potentially break the file system itself and affect the outside systems or the outside containers or applications, because the kernel at that level has no understanding of namespaces or isolation or cgroups. All it sees is, I have a kernel task that's running, which is effectively just a user space process kind of thing that runs in kernel space, and it doesn't actually provide any sort of isolation. Importantly, it doesn't also prevent kernel exploits. If there's any sort of exploit, not just a bug, but a proper exploit, that can break the entire security model of everything. Once you have entered kernel space, you have completely owned the host system. And this is a huge problem because recently there's been some local privilege escalation vulnerabilities in Linux. There's some corruption bugs that we'll talk about with NVIDIA and things like that, where you can effectively get code execution inside the Linux kernel. And this is extremely dangerous and effectively breaks all of the security model of Linux, which is a fairly weak security model to begin with. It also doesn't really protect you from system call abuse. There's other systems in Linux that try to do this, setcomp being one of them. If you know anything about setcomp, you probably are groaning because it's awful and really hard to use. And like usually you have to basically profile your application to produce the amount, the kind of profile of system calls you want to allow. It's not great, and it doesn't really solve any of the actual fundamental problems of Linux. It's basically just locking things down to only what you need. But if your application is using a lot of those system calls, and in a way that isn't really restrictable, you're still vulnerable. You're just effectively reducing what the attack surface at that point. And it also can't contain side channel leaks. If a side channel leak is possible and through any sort of method, because it's a shared Linux kernel, all of that vulnerability is still, an attack surface is still available to it. And I talked a little bit about this already, but cgroups are accounting, not policing. So, or policing, policing, whatever. So cgroups limit resources. They don't prevent abuse of the kernel. So what they're primarily focused on is limiting things like how much file I/O you can use, or how much memory you're allowed to use, or how much CPU you're allowed to use. But because of the architecture of the Linux kernel, this doesn't really work so well. Not in reality. You can get approximation, like, for example, if I run a process and I limit the CPU, I can limit the CPU that the application uses, but that application makes a system call into the Linux kernel, and then that has a second order effect that affects something else in a kernel task, for example. There's no way to isolate that CPU usage that's being used to service that system. So going back to my Btrfs example, if you, for example, turn on compression in Btrfs and then you write a large file or something like that, that CPU is not accounted to the application that's writing that file, because that compression is happening asynchronously in a kernel task. So you get all sorts of really wacky ways of dealing with the accounting of resources. And a tenant can still make system calls against the shared kernel and trigger kernel bugs. For example, going back to Btrfs again, if you have a bug in the Btrfs, which for a long time was basically every release had a major bug in Btrfs, you can trigger some really nasty bugs and potentially even kernel oops or kernel panic the system. And the tenant can still affect the scheduling and caching behavior. Just because you're limiting the resources doesn't mean that you are not having an effect on the scheduling decisions of the system, particularly when we're talking about really advanced scheduling algorithms and complicated CPU scheduling in Linux and skegexed and other eBPF curse things you can do. Those kinds of things, they can only have a limited effect on the system, and you can really only affect those things through cgroups in a very limited way. And so multi-tenancy via namespaces and cgroups is basically multi-tenancy by politeness. As long as you are polite to the kernel, everything's going to be fine. But that's not the reality that we live in. So what does the shape of the problem look like? If you have a shared kernel and you have many tenants in a single boundary, you have multiple tenants that are effectively running in their own namespaces and cgroups. Hopefully this is visible. And that shared Linux kernel is just effectively like a single process that everything talks to, and everything, it's not a process, but it's the kernel, but you can think of it like it's one address space effectively. Now, that comes with a lot of caveats, but when you really look at it, it feels like one address space. And it's huge. I mean, the Linux kernel attack surface is absurdly large, and we're not just talking about system calls. We're talking about drivers. What can you access when you have access to the sysfs, for example? What can you affect if you can load a kernel module, which is basically complete code execution into the kernel? What can you affect if you have access to something like a GPU driver, which is, by the way, one of the scariest things that scares me about multi-tenancy today is that people are doing just containers with GPUs and then lending them out to multiple different people and expecting this to be fine. I can tell you that GPUs are not at all designed for this, but that is realistically what people are doing today in some environments. Ultimately, a single bug that affects the kernel in one of these tenants can break the entire system. And you can't trust anything that we have in the Linux kernel. We just fundamentally do not have a concept in the Linux kernel that really provides that degree of isolation and security that you can rely upon. So let's talk about CVEs. This stuff scares me to death, but leaky vessels in 2024 was a huge one where host file system access was leaked via file descriptors. I think that one's really interesting, and the CVE is here if you want to go dive into it. But to be honest with you, the NVIDIA ones are the ones that are most interesting to me on this list, primarily because NVIDIA and the kind of container architecture that people are trying to use with GPUs, a GPU was originally created for graphics rendering. It was created to render the desktop on your machine, not to run applications on. And so that same GPU driver that was doing the rendering for your graphics, which does not require basically any security at all, is now being required to have a secure mechanism, which it doesn't. And so you basically get a GPU driver that is really easy to break, really easy to affect, potentially escape from a container and things like that, but more importantly, crash the system. I have personally seen GPUs quite literally break the firmware on the GPU and then cause a kernel panic. If you are running in a system where you are sharing GPUs with different people and you are not using any sort of hypervisor-based isolation, which we'll get to in a minute, this should scare you. The other thing that's really interesting on this list is run C. Remember how I said that containers aren't really a thing in the Linux kernel? Well, container runtime developers have to do a ton of work to make you think they are. And one of those things is that they have to mask the paths in sysfs and dev and proc and things like that. So there's quite a lot of basically agreed upon files that we literally just mount dev null over in order to make it impossible to effectively break or access the kernel in a particular way. This is really, really gross, and it's basically because the Linux kernel does not have any sort of way to isolate those things. We basically just brute force it by literally mounting dev null. In some cases, we will mount, in like run C, we'll mount like an empty directory onto certain directories in sysfs. This comes with a huge problem. What if I make a kernel that has a new feature, that happens to accidentally break the system. I have then created a container exploit that I didn't even know because I'm just a Linux kernel developer or whatever, and I create some new feature. Let's think IOU ring was a very famous example where for a long time, IOU ring had no visibility whatsoever from a lot of security tools because it had kind of a different way of handling system calls. But what if I do that on the file system? Suddenly, run C's security mechanisms just completely break. There's a whole bunch of other interesting things, Linux kernel. These are the less recent ones, or relatively less recent. And then one thing that is also on this list is Firecracker. And one of the reasons why this is listed here is because I wanted to explain that just because you have a MicroVM, which we haven't even really dived into yet, that doesn't mean that you are immune from these problems. It just means that the attack surface changes. In this case, Firecracker was vulnerable to a PCI vulnerability. So you might have seen the recent news about things like copyfail, dirty frag, fragnesia. I'm sure like 7 others have dropped since I've even been on this talk. But like this stuff is really scary. Whatever you believe about the AI models today, or Mythos and how good it is or whatever, the way that people are thinking about vulnerabilities is changing. Whether or not the models are good enough for this or not to find these kinds of bugs is sort of irrelevant to me. What I'm recognizing in the industry is that people are more interested than ever at finding these types of bugs. And there's going to be more of these, a lot more. I think every time I have walked to the conference here, I have thought of some scary new thing that I want to research in the Linux kernel that probably has some vulnerability or something. And there's many more vulnerability researchers that are probably thinking about stuff like this as well. So I've told you all your problems. So what do we do about it? As I said, I'm not unbiased, but the MicroVM, I think, is the only real way forward at the current moment. There's a lot of research in this area, but I think this is the best we've got. And ultimately, what this is about is giving every workload its own kernel and enforce it via hardware. We need to assume malicious intent from everything. It doesn't matter how much you trust your code. Pretty much everything is vulnerable these days, whether you know it or not. I mean, think about all the language runtimes you're running in production. Think about supply chain attacks. Think about the Linux kernel vulnerabilities that we were just talking about. Everything, there's now no application I can think of that is not vulnerable to some sort of attack of that sort. You need to isolate everything so that a kernel compromise doesn't affect other applications. And I think this is not just for when you don't trust your code. Again, this is for even when you think you trust your code. I think everything is now at risk. You need to build thin trust boundaries where you have a high degree of confidence in the security of the system. We need to actually architect our systems to handle the worst case scenarios, because those worst case scenarios are happening to us right now. See those CVEs earlier. And you should not have to change your application to effectively get this kind of security. I think that although I think WASM is really cool, one of the problems with it is that to adopt WASM, sure, there's like compilers and things to build WASM stuff, but you still have to think about the fact that you're running on WASM. Like you're getting a different interface, you're getting a different environment, and you have to think about it. The cool thing about a MicroVM is that you should not have to think about those things. And the blast radius shrinks from the node to the workload. So if you have a MicroVM, you can run with the kernel in every single MicroVM. Here at Edera, we call them zones, so I'm using the zone terminology. And we also have a type 1 hypervisor in our architecture where we basically have a hypervisor that runs directly on the hardware that can natively run containers as is with hypercalls and all of the various things that allow it to do that efficiently and highly performantly. And importantly, if a kernel bug or an exploit in the application occurs, that is contained to the actual kernel that is associated with the zone. So let's talk about the shared kernel versus a MicroVM. With the shared kernel, you have one Linux kernel and many tenants. The boundary that you get is namespaces. If you exploit one container, you effectively can reach all of those containers. The big advantage, though, is that it has the fastest startup time, highest density. Because it's just processes, it's effectively polite isolation. And with a MicroVM, you get a kernel per tenant. You get a hypervisor-based boundary. If you exploit one, you can only reach one. And it's fast enough, and the density is sufficient. In fact, in some cases, the density can actually be better than shared kernel if you architect it correctly and you use the right tools. Let's look at the landscape a little bit. Probably most people are familiar with Firecracker. It's used in AWS Lambda, has a fast cold start. The cloud hypervisor is sort of, I guess, a very simple KVM-based solution. Firecracker is KVM as well. It's written in Rust and basically doesn't have any of the QEMU device models, but also has features. One of the things that Firecracker does that's kind of strange is because it's made for AWS, it's a little bit like featureless and really designed for you to build on top of. You have kata containers, which is basically all about Kubernetes. I think basically 99% of people there using kata containers use Kubernetes. It's effectively just the container like CRUD, I guess, on top of VMs, and then it uses other backends like Firecracker or Cloud Hypervisor. And then, as I said, I'm not unbiased, Edera is all about Kubernetes. We also run containers and VMs, and we also support GPUs and other things. And the cool thing about us is that you can get MicroVMs without even requiring hardware virtualization or nested virtualization. And we also contribute to projects like Zen. If you're familiar with Zen, we also support KVM as well. And do want to note that Edera is a commercial product. So I added a slide here for me to rant a little bit. I've got 2 rant slides. I'm going to keep it very simple because I'm actually doing better on time than I thought. But I think it's very important that people take this seriously. There's many conversations that I have where people have very incorrect ideas about how these systems underneath them work. And as an application developer, I think it's really critical that you understand more about the system that you are running on, because I gave a whole talk on this point, but the layers that exist underneath you as an application developer heavily affect the security of your system, more so than probably even your application code. If you use Linux incorrectly, you will be vulnerable to some of the nastiest bugs you've ever seen in your life, nastiest exploits. It is very dangerous. And I've seen some things, let's put it that way. And the industry does not take this seriously enough, and this year is the time to fix it because it's not getting any better. So I'll not complain too much to the application developers, and instead I'll talk to the systems developers, the kernel people, the people developing any sort of isolation technology. You need to build things that people can use. One of the reasons why I started Edera was primarily because I saw the tools that were on the market, and no one had really made something for others. It was always for themselves. And we have to rethink how we build the Linux kernel itself, how we build hypervisors, how we give tools to people and what they can use to solve these problems fundamentally. A very common refrain that I hear from people is, I just don't understand why the Linux kernel doesn't do this for us. And I mean, the Linux kernel, if you really look at it, it's a mass kludge of various different things trying to do and serve various different people. I think it's likely that some sort of solution for this will make it upstream into Linux one day. I think it's going to fit about 5% of everyone's use cases, and it's going to fall by the wayside and not get used. Because I think that we have to really focus on what matters most, which is where the honest trade-offs come in. So cold start times are probably the biggest thing that people ask about, we talk about. I'll just tell you from personal experience, most people who think they care about cold start times actually do not care about cold start times at all. The vast majority of people who think that cold start times are their problem probably need to actually just reduce their container image from 40,000 gigabytes to 500 megabytes or whatever. So the times that I have quoted here are an image that has been pulled, and in Firecracker's case, it's Firecracker Containerd, because another part of the rant that I was going to mention is that Firecracker won't save you. And that's because Firecracker has nothing to do with containers. It is a VM runtime. You have to build the containers on top of it. And by the way, also the paper mentions like 25 millisecond start times. That's not realistic. But Firecracker takes about 1 second to start a fully pulled container image. That is actually good enough for 99.99999% of use cases. With Edera, I might be able to show you a demo, we'll see. But you'll see that it starts in about 600 milliseconds. With Docker, you're getting about 400 milliseconds. I think I've seen it as low as 100 milliseconds, but Docker is highly variable. Probably has something to do with Go, if I had to guess. Yeah, like cold start times are usually the caveat that you have to add to MicroVMs. I'm going to just tell you it's probably not as big of a deal as you think. Memory overhead is another interesting thing. You might have had the question like, oh, if there's a kernel in this thing, does that add extra memory? The answer is for most VM runtimes, yes. There will always be some amount of overhead for running your own Linux kernel in every system, or sorry, in every workload. At Edera, we do some really interesting things like using paravirtualization, bypassing certain mechanisms in the Linux kernel, compiling out a bunch of stuff. Our theoretically possible overhead is tens of megabytes. We think that we can reduce it with copy on write pages and things like that to kilobytes, maybe. So it just depends on what you're doing. There's no easy number to quote there. Nested virtualization, if you're not using Edera, basically, and I think gvisor, although I don't consider gvisor is not a microVM, but it is a way to run an application in a way that it bypasses the kernel. Nested virtualization is almost certainly required. One of the reasons why I started Edera is because I did not have nested virtualization on the platforms I needed to run on. And so I wanted to make sure that it can run in multiple places. And the device pass-through is just like, I think Edera is probably one of the few that has invested a lot of time in it. Kata has a few things, but it's still very messy and uses QEMU and is a giant mess. But like device pass-through is a huge problem that basically we had to have investments in it because I don't know if anyone's ever passed through a GPU like to a desktop VM or something. I know a lot of people tend to do that. It works about 90% of the time, and then like 10% of the time it just explodes. And luckily in the server space it's a lot better. But what you get in return for all these trade-offs is a boundary that your threat model can actually rely on. I'm running short on time, but some non-obvious things that people forget when you're running with MicroVMs, eBPF just doesn't work with multiple VMs out of the box. Edera has focused on integrating with eBPF vendors because people want visibility even though it is isolated. And so, for example, we integrate with Falco natively on our platform. This is a thing that I think most people who try to create a startup or some sort of project around MicroVMs, if you ignore this problem, everyone's going to ignore you. Some platform infra tools rely on a lack of security boundary. And realistically, like everything that runs in Kube system seems to, on Kubernetes, seems to want to have host PID or some sort of nastiness like that. You can run these on workloads inside of a host, but with Edera, your Kubernetes host itself is actually isolated as well. So you get some of the advantages of it not running like in the most privileged mode possible. Resource management becomes a little bit harder to predict. Particularly with KVM-based solutions, your VMM has a lot of overhead because it's effectively just a process. So we spent a lot of time at Edera focusing on low overhead interfaces and scheduling to kind of compensate. This is kind of hard to see, but essentially what this is trying to show is that the blast radius of a system that is running on a MicroVM or in what we call zones in Edera, when they have the kernel directly associated with the tenant, the blast radius is significantly lower. The hypervisor is a very thin, trustable layer. Then the kernel itself is untrusted. And so the only thing that you actually have to trust is the type 1 hypervisor. Our stats put us at like 98% reduction in attack surface if you run your applications like this. So what are the takeaways? There are production-ready MicroVM platforms today. This is not a theoretical thing. Obviously, I'm biased, and Edera is one that I think that everyone should use, but I think that investments are being made in this space. Containers are not a security boundary. The Linux kernel probably won't save you, at least for another 10 years. Another namespace won't save you. I think I didn't even go into this really, but a lot of people think that user namespaces are a solution to this problem, and actually our research shows that user namespaces increase the attack surface in the Linux kernel because you're effectively allowing more system calls to be accessible. And if someone creates some magic namespace tomorrow, it's not going to save you either. Just another namespace, bro, and it's not going to work. And I think for the application developers, the biggest thing that I feel strongly about is that you should know how your containers run. You should at a bare minimum know if you're using run C, crun, if you're using cryo, if you're using containerd. I think probably most people know those things, but the people that don't, I think it's very critical information. And then dive into what a C group is in the namespace and actually understand that. C groups and namespaces are rarely the solution that you think they are. I'm basically at time, so thank you. Yep.
I guess the question that's still open is contrast MicroVMs with standard VMs.
Yes, I did not touch on that very much because it is very hard to explain this in an intelligent way quickly, but yes. So the quick answer to what is the difference between a MicroVM and a standard VM is actually not much. I think a lot of people think that a MicroVM is like some fundamentally different thing, but the problem with VMs and why they were heavyweight and why people ditched them had a lot more to do with the tooling and VMware and things like that than it did with the fundamental way that VMs work on the hardware level. Interesting fact is that you can actually, on Intel hardware, create a virtual machine context in nanoseconds. Most people would probably think it's like a few seconds if I asked them. But the way that we as system developers use VMs on the hardware has always been the problem. And what MicroVMs are doing is effectively cutting out a lot of that legacy stuff that requires all the time. So think about VMware specifically. They have to emulate a lot of hardware and have to do a lot of things like emulating SATA or IDE and things like that. Virt.io and things like that solve those problems and really cut out a lot of that kind of overhead. But that could honestly be its own talk. It'd probably be a much more advanced talk because I'd have to go into a lot of nerd stuff. But I think the important thing to remember is that MicroVMs and the way that you can use them today is actually very lightweight. And VMs as a concept are not fundamentally flawed in any sort of way that makes them heavier weight. It's purely just how we design them.
Would a fair distinction be the traditional VMs try to emulate hardware that's not actually there?
Yes.
MicroVM 100% the hardware that is.
Yes. So typically a standard VM, for example, is emulating what is essentially a desktop, right? But when you're running applications, you don't care if there's a display. You don't care that there's a keyboard mouse. You don't care where the disk comes from necessarily. So the biggest distinction is what it emulates. But actually, like VMware, for example, which is probably what most people think of when they think of VMs and heavyweightness, that architecture is just heavyweight because its goal is to run a full operating system, whereas a MicroVM doesn't have to run a full operating system. It can just run the Linux kernel in your application. Cool? Oh.
One last one.
Yeah.
So, presentation today about Zephyr and the concept of pulling out all the legacy pieces and the
Yeah.
features that allow for the universality of the Linux kernel to really
Yeah.
run in hardware. Because virtualization and the security concept, having all of that pulled out makes it a micro-VM. Is that what we need to look to kernel similar libraries?
So I think for practical reasons, my preference is that MicroVMs just run the full kernel. Primarily for compatibility reasons, and because it's easier to debug and more familiar to developers. Like debug experience is a big part of production environments. Library OSs, Zephyr, and things that try to pull out those components, I think, are really interesting and have really good use cases, particularly for extreme high assurance applications. The thing is that, and kind of going back to my rant a little bit, it's very critical that we give people the tools that they understand and can bridge from where they are today, rather than building something that's completely separate and then expecting them to consume it. And so that would, I'd say, is the biggest reason why I think running on just the full Linux kernel is the best solution right now, because it's just familiar and it's the least leap to make the biggest gain. Yep. Yes.
Great talk, Alan. Thank you.
Yep, thank you.
Alex, I wanted to ask you, with MicroVM, if I wanted to get started, like, what solution would you recommend?
Edera is the obvious one, but I think there are multiple platforms out there. It depends on what you want to do. I kind of hated on Firecracker a little bit in this talk, but if you just want to run like a VM image or whatever, Firecracker is perfectly fine. Actually, in my slide about myself, my interest in this topic started from Apple's virtualization platform. I used to kind of, I don't know if I should say this on stage, but I used to decompile all of their frameworks and research all of their virtualization stuff for fun. And so they actually have a really great platform if you want to, from a programming perspective, run a virtual machine. You can just in Swift code, or I think there's Rust bindings and stuff, like start a VM with APIs rather than just a command line. If you want to run your actual applications, though, there are tools out there. I mentioned Kata. That's probably an easy one to access. Obviously, Edera. But I think fundamentally, and I didn't get to the demo, but it's supposed to be simple, but a lot of these tools make it really hard. And actually, maybe I'll just for a second, go a little bit over time and do this real quick. So if I share my full screen here, I will create a MicroVM right now. Here we go. It took 700 milliseconds. So if I just use Edera, I can see, this is a debug version of Edera, just so you know. I can actually see the MicroVM running. I can poke around at it, and I can run a workload. And here's a MicroVM running on Edera today. And if you want to see some nerd stuff, I know it's kind of small, but you can actually see the build of Edera and the HV console as well, because we build on Zen. Oops. I think I broke my debug machine, but anyway, it's you can run all sorts of things in it. There's the Alpine container running. We have all sorts of little things. I guess my point with this is some platforms are more accessible than others, and we focused a lot on UX for that reason, because it's often forgotten in this space. And so I think Edera, very biased answer, but I think Edera is the best and the easiest way to do it. Awesome.